So let's start with generative AI, and everybody knows ChatGPT, so let's use it as a starting point. ChatGPT is based on something called GPT, and GPT stands for Generative Pre-trained Transformer. Let's go through each part. Generative because it creates new original content as opposed to, for example, inferential AI, which is something that classify objects or patterns, or maybe they use decision trees or regression models. This creates new original content. Pre-trained because it's already trained on a data set, so it knows stuff already. And Transformer is a deep learning architecture. It's kind of a specialized neural network, first described in the groundbreaking paper Attention is All You Need, which you need to know the details of this, even though I have a diagram on the right here of encoder-decoder. But you need to know maybe three things, just so that you know why it's called Transformer. First is that it captures relationships between all words, or more precisely tokens, which is like a subdivision smaller than a word, right? So it gives the impression that it understands your input. So that's key in the transformer architecture. But the other very important thing is that it allows for parallel processing of data for faster training. This is pretty much all you need to know, really, if you are just gonna use an LLM in your applications. Now, GPT is an LLM, as I just said, and LLM stands for Large Language Model. You probably know that, but let's go through this. So large because it's trained on a massive data set. It's a chunk of the internet, really. It could be the common crawl, which is a publicly available corpus of billions of web pages. And it has a high number of parameters. More on this in a moment. Language because it's trained using text. And a model because it's a mathematical representation. If you really want to go deep into the woods, no pun intended, you can read this book, Deep Learning. It's not easy to read, but it gives you everything you need to know about these deep learning algorithms and methods and so forth. Now, for us, think of a model, AI model, as a set of machine learning algorithms that are implemented in software. And you download these, or you're running it in the cloud or wherever you want. And they also have a configuration file with something called the parameters or the weights. And the weights are like these knobs that you can tweak in an audio system until you get the desired output. Well, in the same way, an LLM or an AI model is trained on these massive data sets until it tweaks these knobs until it kind of outputs the desired result. It's like a huge mathematical equation. It has tons of parameters in it. And we're going to find through a process of training what would be these numbers so that it produces the desired output. Now, when you use an AI model to answer questions or perform tasks, that's called inference. So the questions is what we call the prompt. That's the input to a model, an AI model, which we call foundation model, for example, GPT. And the model's response is the prediction. So in the case of a GPT, it predicts the next word. Now, the quality of your input, so the prompt, determines the quality of the response or the prediction. So it's very important to play around with that. And I'm not going to say too much about it, but I'm going to show you a quick example. You probably know this. You have played with ChatGPT and other LLMs. But if you prompt an LLM with something like, you are a helpful assistant, how is replication used in this system? And then you attach a PDF file, let's say, with the description of a technical description of a system, software system. It gives you a prediction like this: replication ensures data is always available, blah, blah, blah. But if you prompt it with something like, you're a senior database administrator, and ask the same thing, you get a very different prediction, much more technical, with things that a senior database administrator will understand. And so this means that whatever you input, it's going to determine the output, right? And yeah, this is very basic, and we all have this sense of, how to prompt, but there are many more techniques. Many of these actually are being baked into the LLMs already, but some techniques are not. So I suggest having a look at a book like Prompt Engineering for Generative AI. You will learn quite a few interesting tips there. Now, we are talking about LLMs, and that's what we are using and focusing on today. But there are more models. So, for example, small language models. Now, what's large? A large model today could be a very small tomorrow, right? Here you have some examples, but just be aware that this terminology is out there. You have models for computer vision, for speech recognition. and multimodal. So they combine the other ones. Those are very, very interesting. You can just consume these AI models in the cloud, or you can deploy them yourself too. But so the providers of these models in the cloud, they take care of all the machine learning life cycle. So gathering the data preparation, building the machine learning model, training the model, test the model, deployment. If you want to deploy yourself, you will have to have a look at this, but you can just consume it in the cloud. Now, these models have been pre-trained with a huge amount of data that, well, obviously doesn't include your private data, right? They don't know anything about your organization, your products, orders, or whatnot. However, first of all, you can just train it again, but that's extremely expensive. You can, however, adjust the internal weights of a model by retraining on additional data. That's something called fine-tuning. But this is also expensive, especially because, well, it might require some significant resources, especially for large models. For example, specialized hardware like GPUs and TPUs. It requires maybe kind of long processing times, although not as long as a pre-training process. It requires also a substantial amount of labeled data, and preparing that data and getting this data is not cheap. So this could be very expensive as well. Fortunately, there's a technique which is an alternative to retraining and fine-tuning called RAG. So before we talk about it, notice that this technique is not new, right? People are using it already. In fact, it is one of the techniques in software development that companies should adopt according to the ThoughtWorks technology or radar. Now, what is RAG? So RAG stands for Retrieval Augmented Generation. Retrieval because it fetches relevant data from external sources like APIs, files, databases especially, which is what we are going to use today. Augmented because it enhances the input to the AI model, the foundation model, with this fetched data. And generation because it produces predictions based on moral knowledge and these fetched data. So as you can guess, the quality of RAG system depends on the quality of the data that you fetch, right? So getting highly relevant data and getting it fast is key. Also, you are charged per token. You can think of it as per word that you send to the LLM. More technically speaking, it's per token. So we have like an incentive to use as not as much information to send to the AI. We cannot just copy all our documents or our database, send it. All those LLMs have a really large context window. That's how much words or tokens you can send to it. We still have this incentive. So it's very important to get the relevant data and only relevant data, and obviously fast to offer a better user experience. Now, RAG mitigates some of the challenges with LLMs, like hallucinations. You have probably seen that when the LLM makes up facts, which are not really facts, but it shows them as with confidence. And the knowledge cutoff, right? Because these models are pre-trained until a certain date, and they don't know anything about the public information that's available after that date. So you can provide this new information using a technique like RAG. Now, I could have just changed these and say, you know what? RAG is just prompt stuffing. And this is an oversimplification, but the core of it, it's actually true. So, for example, you can have a template in your software, in your application, which this is going to be the prompt that you are going to send to the LLM, where you put a question, and you insert whatever the question is, and then you give some context, which is this fetched data, which is related to that question, right? The relevant data for answering that question. So it would look like this when you send it to the LLM. And then the prediction is going to be based on that context. Now, cool, but how do we get this data, the related data? Well, for that, let me show you the architecture of our RAG system. So on the one hand, you have a gigantic data set like the internet, Wikipedia, books that's used to pre-train a foundation model like GPT, Llama, Mistral. And on the other hand, you have a user, which can be a human or it can be another application, that introduces some input into your application developed in Java, Python, Node.js, or any other tool, or a platform or programming language. And you somewhere have also your data. Let's say it's MariaDB, your database. Now, we want to use the LLM to produce the output for this user. But first, let's focus on when the user is trying to write something. For example, they are trying to update the description of a product. So that's what they sent to our application. We take that input and send it to another AI model, which is called the embedding model, which is usually produced by the same people that produce the foundation models. Now, this input is just going to be the same string with the updated description. Just that string with text. We send it to the embedding model. There are some examples of names of embedding models. We're going to later use text embedding 3 large from OpenAI. Well, you send that there. You get a vector. We're going to see what a vector is in a moment. The important thing is that you store the input, which is the new description for the product, plus the associated vector. So it could be a foreign key to the product ID, for example. You store both. We're going to see it in detail later. Eventually, all descriptions will have a vector. Okay, that's the goal here. If you already have tons of products and you're not updating by creating them, then you can, or you have them created already, you can just run a batch process that calculates these vectors. The thing is that all products should have a vector based on the description, for example, for the product. All right, now later, the user wants to know, for example, through a chatbot, whether A, the product A works with B. So they just introduce that question there. Does A work with B? Our application takes that input, sends it to the embedding model again. Then the embedding model returns a vector. And we perform a search, telling MariaDB what are the closest vectors to this one that we just calculated from the user input. Then MariaDB returns that data, which is our data, right, in our database, append it to the prompt, send it to the foundation model, get the prediction, and then we generate the output. So now we're using our data with the foundation model. So we're talking about vectors here. Let's see what they are. And a vector is simply an arrangement of numbers like this. So floating point numbers. In AI, they are called vector embeddings or simply embeddings. And an embedding is something that encapsulates semantic meaning about something. So you can think of an embedding as a vector plus some data or a pointer to data. And they are cool because they kind of encapsulate the semantic meaning in a very compact fixed length data structure where it's going to describe some concept, for example, an audio file or an image or a text. It could be a paragraph in a document, a phrase, a description of a product, anything really. Let's say this vector represents this cute dog, very friendly, called Draco the dog. So each dimension here describes Draco in certain way, right? Each number represents certain feature. Let's say, although this is not exactly like this, but bear with me. Let's say this is the representations. So the first one is how canine he is. So he's highly canine. If we consider maybe these numbers range from -1 to +1. Not very feline, a little bit human, not very fast it seems, and also not very big. So we're representing the meaning of this dog, of Draco, in a single vector. Now we can take another one, for example, Mina, the cat. So she is less canine, obviously, more feline, and apparently it's less human, but it's faster. Also, it's not very big. You get the idea, right? Now, I said that this represents these features that we can map directly into concepts in our minds. That's actually not true. When we are using an embedder, like the one provided by, say, OpenAI and others, we don't know what these things mean. And it doesn't matter. We don't have to. We don't use these dimensions, it's called each number, individually. We use the vector as a whole, and we operate on whole vectors, okay? Remember, there are thousands of dimensions here. I'm showing just very few here, and I made up some concepts, but I just wanted to have clarity that that's not the case, all right? But we can think of it a little bit like that. There is some meaning, it's just that we don't know what the meaning of each dimension is. The neural network, when trained, it came up with these things, and it means something mathematically to to the model. Okay, so because we have thousands of dimensions, we need a proper way to store these and operate on these. So let's talk about vector databases. And for a long time, we have divided database systems, generally speaking, in two kind of databases. One for our transactions or the daily operations of our applications, where you store things in rows. Another one for analytics, where you store things in columns, so you can operate faster on all the values of individual columns. These are two types of databases. And now one type of databases that's gaining a little bit of attention is the vector database, where you have the dimensions here, your vectors, and then a payload, something associated to this vector. This is cool and everything, but the problem is that each one has its own SQL dialect. Moreover, maybe the vector database doesn't even have a SQL dialect. That means that your application needs to understand and use this. You as a developer need to understand the SQL dialect 1, the dialect 2, and this new API. That also means that you will have to download different connectors or drivers or modules or libraries to connect to these different databases. You need to deal with 3 different providers of databases, each one with different policies, with different release policies, with different qualities, with different even vocabulary, and you have to learn all these. Now, the connectors also, or the drivers or modules or libraries for your programming language, you have to keep an eye on the releases of these drivers as well. So you get it. It's a whole lot of extra complexity when you add these systems. Now, MariaDB has a different approach to databases, where we have storage engines. So the powerful InnoDB for transactions or the operations, and column store for analytics. And they live in the same server. You don't need an additional server. In fact, if you install MariaDB and you run show engines, you see that there are some storage engines already there for you to use. And you can add additional ones, install and enable additional ones like column store and, for example, MyRocks and others. Now, something cool about this is that you have a single SQL layer here. So your application only has to deal with this one single connector. And you can run cross-engine queries, meaning in one single SQL query, you can involve tables that use different storage engines. That's a pretty cool feature in MariaDB. So this is very elegant. Now, on the vectors side, well, you can just store them in some column in this table, for example, and there's a data type for that called vector. So this is a very elegant solution to databases for AI applications where you don't need to introduce a new vector database. MariaDB is a vector database. So let me show you an example of how to store vectors in MariaDB. And for that, I'm going to use this example. So thinking about thousands of dimensions is too difficult. So let's use 2. So we can use these 2-dimensional space. And we're going to put some objects here. Let's start with the alarm clock. So this one, for our purposes, is very small and not very fast. A cow, on the other hand, is much bigger and has more speed. A bicycle, maybe it has more speed. It has potential to have more speed, depending who's biking, but it's not as large as a cow. And, well, we have an eagle here with even more speed and a bit smaller. Don't take this too seriously, but we can add some coordinates here, right? These are silly examples, so we see the relationships between the objects in the 2-dimensional space. Now we want to store these in our database, so let's do that. We first need to create a table. We're going to call it objects. We store the name, and then we store the embedding or the vector. So the embedding is of type vector, and in parentheses, you specify the number of dimensions. We have 2 dimensions only. We can say insert into objects name embedding, and we insert the values. So for the alarm clock, we introduce the coordinates, but first we pass them through a function, which is called vec for vector from text. And this transforms these JSON array of numbers to the format that MariaDB uses to store this vector, which is just a float sequence of bytes. It's much more efficient. And you can do the same with the other objects. Very simple. With that, you have stored your vectors in MariaDB very efficiently. But what's the point of this? Why are we storing this? So that's because we want to perform similarity search. So let's talk about it. Let's get back to our example, right? So you might have noticed that on this region, you are going to get all the big objects. and in this region, the smaller objects. Likewise, on the left, you'll have the slow objects, and on the right, you have the fast objects. So that means that the geometry of this space tells us something about the objects, how similar they are, at least in terms of size and speed in this example. So the relationship of where they are tells us something, right? So these two are more similar than these two, and we can use that to perform similarity search. So let's say we want to find from what we have in the database, what's the closest one to this one? So we can say select name from objects, order by this function vector distance Euclidean, which measures the distance between two vectors. So the first one is, well, the thing that we're interested in, and then each embedding is stored in the database. Now we can say just limit one, we're interested in the closest, in the most similar object to something small and slow. So this is obviously going to give us alarm clock. And in fact, if you run these on MariaDB, that's what you get as a result. You can do the same for another object, which in this case I call big and semi-fast. And of course, you're going to get cow in this case. You can run these examples in MariaDB and check that this is actually what happens. It's pretty cool. No magic here, right? Very basic similarity search in terms of size and speed. So to run similarity search, what you do is you convert data to vectors using an embedding model. And by the way, I'm using text, but it could be image or audio. And then you store these vectors in a database like MariaDB. You might want to create an index if you get a certain number of vectors in your database, for example, millions. Then you will have to create a vector so it's fast. Remember, this is thousands of dimensions. So it's computationally expensive, but MariaDB has a very powerful index that allows you to search faster. So in order to search, you convert the user input to a vector using the same embedding model. You cannot use a different one. It has to be the same number of dimensions, and well, the same meaning, whatever is the meaning of each dimension should be the same, and that means using the same model. Then you find the closest vectors in the database. That's where you would use the index. And when you use an index in MariaDB, the search is approximate. So let me show you how to define an index. This is the syntax. So first of all, remember that you can have only one vector column per table. Second, that needs to be not null if you are going to create an index. So with that, you can use this syntax to create it, vector index, give it a name, whatever you want, the column name, and then a set of parameters or options that help configure the index. You can think of these as a setting that influences how the database searches for similar data. So this one, M, is like a trade-off between accuracy and resource consumption. So a higher value for M generally means the search results will be more accurate, but this comes at the cost of slower search times, that's reads, and slower insertion times, so that's writes. It also means that the index itself is going to be larger and use more memory. So it's a trade-off. Then you have the distance function that this index is going to use. Previously, we used Euclidean distance. Now we are using cosine, which is a better option when you are comparing the meaning of text. This one measures the angle instead. That's another way of telling how two vectors are similar or not, or how similar, rather, they are. Okay, and if you have the data already, you can use the create vector index syntax that is shown here. I will refer you to the MariaDB documentation. You have a link right there for more information, more details on all these. And just really quick through this, I'm not going to talk about this too much. There are variables, configuration variables that you can use to tweak how MariaDB behaves in terms of this index. And these variables all start with MHNSW. So HNSW means hierarchical, navigable, small world. And the M is for MariaDB. So it's a MariaDB implementation of these, which is for robust, approximate, nearest neighbor search. This is state of the art, and MariaDB happens to have one of the fastest, if not the fastest, according to benchmarks by us and by others, by the way, compared to other databases, super fast. All right, so let me show you the demo now. And like I said, it's going to be some screenshots. But let me introduce it here. So we're going to be building a product recommendation chatbot. You can find the code for this on GitHub. We're going to use MariaDB 11.7. with one table, which is populated with around 1,000 rows. We're going to be using the OpenAI API with the text embedding tree, a small embedder, the GPT-4o mini, that's the LLM, and that means that we will need an API key. If you want to run this, you will have to generate one. We're going to use Java with no frameworks, and these are some of the tools that I'm going to use to kind of make it look shorter, the code, but it's not that short, I have to say, compared to what you would get if you use a framework. So I want to give you a word of caution here. Don't do these in your office. Do it at home for your own experiments. Don't do it at the office. Don't do it for production. Use AI frameworks. But the reason I'm doing it like this is because then you can see that there is no magic and it's just consuming a REST service, a couple of REST services. And you are able to follow the execution of each step and getting to know what's happening under the hood. Okay. So first, we have, this demo has one program or two programs. The first one is called Compute Vectors. And also we have a MariaDB database with these table products. And the Compute Vectors program is going to take a product, more precisely like the title, description, the price, and some other columns there. And it's going to send that to the OpenAI API. This is going to use the embedder. So it's going to send this as a string. It's going to concatenate these values as a string, send it to the embedder in OpenAI, which gives us a vector. Then we can store this vector in MariaDB. We put this in a for loop, and then we complete all the products. That's the preparation for the demo. Okay, all products have now a vector. Now there's another program, Chat Demo, which takes the input from a user. They want some shoes apparently, and sends that string to OpenAI, the embedder. Now that again gives us a vector, and then we can prepare a SQL query using the distant functions, order by a certain number of products, and MariaDB is going to find the closest vectors and then return the associated data to our application. So we can take those products and send them to OpenAI, this time to the LLM endpoint. So in the form of a string. So I want shoes from the following list, and we append all the products that we found with the similarity search from MariaDB. Then we get an answer, which is a string, and then we show it to the user. So that's going to be the recommendation for the product. Okay, so here's my IDE. The first thing is that I do is just I run Docker Compose up, which is basically this file. Just regular MariaDB deployment with Docker Compose in this case. But interesting things that we have an schema.sql file in the Docker entry point initdb.d directory. That means it's going to be run automatically when the container starts. And this is the contents of this file. So we're creating a table, products with tons of columns. And if we scroll down a little bit there, we see the embedding column, which is a vector with 1,536 dimensions. That's what OpenAI, the model that we are using from OpenAI, there's another one, gives us. If we scroll a little bit more, then we see that we are loading data from a CSV file, and it happens to be products from Walmart. So at that point, we have database ready. Now let's go to the Compute Vectors program. And if you're not a Java developer, you're not interested in Java, just you need to, even if you are a Java developer, don't pay too much attention to each single line of this. I'm just going to highlight the steps. Like I said, you can find the code on GitHub. So first we need the embeddings URL. So you can see it's api.openai.com version 1/embeddings. That's the embedder. Then when we consume this endpoint, this REST service, then we have to send which embedding model we want to use because there are several. So we are going to use text embedding 3 small. Also, we read the API key that I generated online on the website for OpenAI API. And I define that somewhere in my operating system as an environment variable, and I'm just reading it here. So I can use it in my program because I have to send that when I consume the REST service, obviously. Now, later, when we run this program, then we connect to MariaDB, and we run this query, right? Just pay attention only to the query here. So we're selecting the ID from the products table, and also the other column is just a product, something we call product summary. And the product summary is just a concatenation of of a bunch of things like the category name and the final price, rating, and the description as well. Basically, this gives us these kind of results where you have these two columns with the ID and then a bunch of text with a description for the product. Okay, now we scroll down a little bit more. We iterate over each row from this result, from this query, and we prepare the request body for this REST service, right? The important thing here is that I'm going to use the product summary that we got from the database. So for each product, we're going to get that. Then we invoke the REST endpoint. I know this is more complexity. It could be made much easier with, for example, Spring Boot, but I want to show you each step. Just keep that in mind. Here, the only important thing is that we are calling the REST endpoint for the embeddings. We're sending the request body and the API key. Now, basically, OpenAI returns this. So the foundation model will return something like this. It's a JSON object. So we need to navigate through this object and get the embedding attribute here, which you can see it's an array of numbers. That's our embedding. We got it. So we just need to extract that and store it in the database, which we do here. So I'm running an update, and I'm using JSON extract just to navigate through that JSON and get just the embedding, right? That's it. We're updating the product, and we are iterating over all the products here. Now, when you run this, then you're going to see how the products get updated, their vectors, and eventually the process is completed. And now we can see the other program, chat demo. So this one also has the embeddings URL because we need them, but we need also a chat completions endpoint. So notice how that URL ends in chat/completions. And the chat model, it's going to be GPT-4o mini. Now, when you run this program, it's going to ask for what you are looking for, right? So we can type something like this, summer shirts for kids, right? It's going to say, okay, cool, I'm going to find the closest products. The first thing it does is it gets a vector for this string, summer shirts for kids. So it sends it to OpenAI. I'm not going to show that in the code because it's similar to the previous one. But then later, the other thing that's going to do is similarity search through SQL. So here we are using the cosine function, and we are using the vector that was calculated from the user input to compare with all the vectors in our database. And we have a limit 10 right there. That's going to be, we have 10 products. Then it's going to try to generate the response. So this is two things. First, we need to build the prompt. So we are saying, hey, you are an expert sales assistant. Help me choose the best product for my needs. Recommend only one product from the list below and explain why it's the best choice in one short paragraph. Spend some time crafting this in the best possible way. Use a prompt engineering for that, or the techniques provided by it. And also you need to experiment a little bit, I have to say. Well, then we say, I'm looking for, and we're going to inject the input. And then we say, well, the available products is the context. That's what we got from MariaDB. It's just a string, and we concatenate all the results there. Basically, what we are sending is something like this, right? So it's the same thing, but you can see that it says I'm looking for summer shirts for kids, and then we are just appending all the available products. This is what gets sent. It's like you've copy-pasted this to ChatGPT. That's what we're going to do. And that's here. So we form the request. As you can see, it's using the prompt that we just created. And notice also that you have some additional configurations here. So temperature is how creative the model is going to be. So more deterministic or less deterministic. And max number of tokens. This is important too, because again, you are charged by the token. Then we are going to get the response. And it says, I recommend the Disney Boys graphic tee, Donald Duck, short sleeves t-shirt, blah, blah, blah. So it makes sense. It's using our data. So we can try to find this. It actually, the prompt also tries to sell it to us, right? So this shirt is the best choice for summer shirts for kids because blah, 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 blah. That's the job of the LLM. Now we can check if this product is actually in our database, which it is. So it's using our data. Okay, so this is RAG in action. Some key takeaways before we wrap up. Remember, fine-tuning AI models could be very expensive. RAG is not. And the core of it is just vector search and prompt stuffing. It's more than that, but this is the core of it, right? Vectors store semantic meaning, which allows us to perform vector search, which finds relevant data. And MariaDB simplifies application development because you need to introduce additional systems or databases. Now, use AI frameworks. In fact, I have a screenshot of what it would look like with Spring AI. It's much shorter. That's the way you should do. This is the compute vectors program. I'm omitting some parts there, but you get the idea. It's cleaner and it takes care of the actual implementation details on different LLMs and different vector stores. MariaDB has an integration to this, as well as other frameworks. Okay, I also promised to show you a roadmap to AI, and I'm not going to go through all these. So take a screenshot of this, or even better, download the slides. I think there could be an option somewhere to download these. If not, then let me know and I'll provide it. But let's just describe very quickly some of these. So in the neural networks field or the machine learning field, if you want to learn about what a neural network is, you can implement an XOR function, but that's, I don't know, I tried it and it's really boring because you can use just an operator from your programming language, so you don't see the utility. So this is much better, the handwritten digits. So you can program a neural network that recognizes handwritten digits, and there is a database with that name that's available with tons of digits, and they are labeled. That's a very interesting exercise to do. It's like the hello world of neural networks. On prompt engineering, yeah, take a look at the techniques there. This is mandatory. Maybe you know this already, one-shot and few-shot learning, where you give like examples of input and output, and then you send the question, and it's going to follow that pattern that found from the example. So one shot is like one example, few shots, like several examples. But there are other very, very interesting techniques here, like ARR, which is like analyzing, retrieving, and reasoning. So basically, you explicitly ask the LLM to analyze the intent of the question and then retrieve the relevant information and reason step by step. And just by telling the LLM this, it results in better predictions. Okay, on advanced RAG techniques, check out ranking, which calculates a matching score that can be utilized to rearrange vector search results. Question rewriting could be very interesting, and some AI frameworks offer the tools for this. So the code's very, very simple. It's like some few lines of code. On agents, which is a very hot topic, well, definitely it's used for tool invocation, right? So it's a way to let the AI model to call external functions or APIs to perform a specific task, such as executing code or interacting with other systems. Definitely check the RAG triad, which are like metrics to measure how well each step of a RAG system is performing. On security, definitely check for prompt injection, which is the equivalent of SQL injection in the AI world. On this distributed inference, if you are planning to deploy your own models, then check how to do parallel processing. I actually want to try this in my famous Raspberry Pi cluster. I don't know if they have the compute power to do this kind of stuff, but I'm definitely going to try it with something called local AI. At some point, if I find the time, it could be very interesting. On the frameworks and libraries, well, if you're Java, use Spring AI, or if you are not using Spring, then LangChain for J. The other programming languages have their own equivalent frameworks. And to finish this, well, on the UI front, we want to show results somewhere on the screen, usually a web browser. Definitely check server-sent events and WebSockets so you can show the output of the LLM as it's being generated, token by token. These two things are going to help you implement that. All right, I think that's what I wanted to show you. These are my coordinates if you want to contact me. Thank you.